guys. Doing the pretest, right? systems, okay? And we know that safety systems are comprised of passive and active ones. Go all the way back in the 80s and 90s, it's just seat belts, right? And then airbags, I think, show up in the 90s, at least in the US. My 1993 Civic, my first car, was only have a driver's side SRS. And I think starting in the 2000s, then they required 2 airbags. Passenger airbag is mandatory. And let's see, IAS comes probably 5 years ago or 8 years ago. IAS, which is the active safety systems. So we'll get to that. Okay, so that's kind of the overview for today. So first, let's talk about seat belts.
Everybody knows what happens in an accident if you don't wear a seat.
So let me mute this because so I'll just explain what's going on. So seat belts, they are still the prime. Oh, sorry, not lying. They're still the primary restraint systems in collisions, and let's take first like a big picture view of what happens in a collision, right? So you have a car and you crashing into something, right? I mean a wall. I mean that's extreme, but so here's you crashing into it. So explain to me the physics of a collision. What's going on in a collision?
Deceleration.
Deceleration, a very high G deceleration. So you go from a velocity of, say 60 kilometers per hour to 0. And what's the problem with this deceleration? Not gravity. The momentum, okay? And it has to happen in a very short time. And that's really the problem, right? I mean, if you decelerate over 10 seconds, no problem. But this happens in 200 milliseconds or a second at most. So this is the problem, right? This is the problem. And because, what was momentum? P. So the change in P, the change in momentum is the impulse force multiplied by the time duration it takes, right? So what happens if the force, the force of the collision is proportional to the change in momentum divided by the time. The smaller the time, what happens to the force? Much bigger, right? So as the time goes to 0, it becomes infinity, obviously. So, and this is one of those things that does not make sense in Star Trek or in other space movies, because even if you are in space, momentum still comes into play, right? So when you accelerate really fast, I mean, the forces are still there. Anyways, but the collision, this is the key here, right? I mean, we cannot change that. The momentum, force times velocity, mass times velocity, final, minus mass times velocity, initial, right? I cannot change this. I mean, this is an accident. And I cannot change that. And I cannot change the mass. So the only thing I can do is manipulate this. And that's really the job of the restraint systems, is to prolong this. Now there are also other things that comes into play other than the safety system, which is the crumple zone itself. So the front of your vehicle is called crumple zone. So you need a certain deformation to take place. Actually, the more, the better. So when you see a crash where the car's nose is like becomes half of the length, I think the driver is probably doing better. Not fine, but better, right? Because this crumple zone gives you the time, right? It means that there is some time and there's a lot of energy absorption happen here rather than me, rather than my body and my skull. So this crumple zone is critical. When people design cars, the front structure, looking from the top here, the front structure, like this is the engine, the transmission and all that, this bar that holds the front bumper, by the way, the front bumper is not what you see, the plastic, right? The real structure is the beam behind the plastic cover. That's a real bumper. In the States, we usually call this bumper cover because it's not the bumper, it's the cover. And then this is the bumper. And then if for front-wheel drive cars at least, right, that I noticed, there is this column that becomes a crumple zone, right? This collapse in a front collision. From a side collision, you have the B pillar. This is often called the A pillar. This is called the B pillar. So the B pillar is what protects you from the side. These are often made from stronger material than the rest of the body. In Volvo, for example, that they're very famous for safety. They made it out of boron steel, which is, have a lot of energy absorption in it. So you got the A pillar and the B pillar for the roll also. So when you roll, the way they cast the roll safety, if you look at the car from the front, they have a plate actually coming in and crushing that. That's how they test rollovers. How the cage still protects you in cases where you roll over. So you got the B pillar and the A pillar protecting the passengers inside. This crumple zone is critical. So even though they try to make a vehicle lightweight, sometimes they use multi-materials. They use lightweight materials in places where it's not structurally important. But for the front, you're kind of stuck with steel because steel is just ductile and it has a lot of energy absorption capability. So you're trying to create basically a crushable zone but still protect the human inside. But even with that, we're still stuck with the physics, right? I mean, the physics, the delta T, you can only reduce it so much, and so we need to restrain the passenger from hitting the front. So here goes the seat belt. By the way, you notice that higher velocity obviously require more forces to stop it. And the kinetic energy, in fact, is to the order of 2 for the velocity. So keep in mind braking. The braking it takes to remove the energy for 100 kilometers per hour versus 50 kilometers per hour is not twice. It's how much? So this is double the speed, but the energy, the kinetic energy you have to remove to the brake is how many times? If you go twice the speed, how much more kinetic energy does that have? compared to 50 kilometers per hour. It's to the power of 2. So if you're going twice the speed, the kinetic energy is 4 times more that you have to dump into the brakes. If you're going at 3 times the speed, say, 50 kilometers per hour versus 150 kilometers per hour, the braking energy you need to dump is 9 times. So it comes down to really discipline in your speed limits. Alright? So that's why even I love to have fun with my car, but I don't go on high speed adrenaline. That's just I have wife and kids. So I have fun with the handling, with acceleration, with braking, but I don't go 150 kilometers per hour. That's just like one policeman once stopped me for going that fast in the United States, and he says, "Sir, you're not driving the car, you're aiming the car." But I mean, it is indeed the real danger is there. You have to remove 9 times the heat, dump the heat to the brakes, and you're just not making it. All right, so back to restraint system. So with all that braking, driver discipline, and crumple zone protections from the cage, we still need to handle the restraint. And here goes the seatbelt. Okay. Okay, so the video starts from kind of building the design from a very basic design, how you first would create a seatbelt system. You need of course, a retractor, because otherwise you're not going to retract it, right? So once you put it, when you release it, it has to come back. So that's just a spring. But now, how do we lock it? So how do we lock the belt? So the lock is provided by this ball and the latch system. So you notice the ball itself has a mass. Now the car is going that way, and when you go into a crash, and the ball's momentum will push itself there, and you notice there is this cage, okay, which kind of, it becomes a cam mechanism, right? The ball pushes on that, and the whole thing is kind of lifted up, and now you catch that. So that's how you get to crash and the seatbelt locks. Now, there is one more problem though. You cannot check it, because then you have to crash the car or go into sudden deceleration for that to kick in. So they make a second mechanism, because remember, the first time they put this on the market, I mean, people are just hesitant to, it's annoying, right? It is annoying, at least to me. So we need a way to persuade them that this is working. And here's the second mechanism. It has a centrifugal effect throw to this additional plate. So if you pull it hard, it's gonna throw this cam into the tooth, the internal tooth, and it's gonna lock it in place. So as it rotates fast, the centrifugal effect will actually throw it out, throw this mass out. If it rotates slow, then nothing happens. So this is what happens when you pull it fast, right? You ever check that? Right. So, but I also noticed that hard braking, try to do a hard brake and pull on your seatbelt. You don't have to pull it fast. You pull it slow, but it also locks. So that's the ball, right? So you got the ball mechanism and this rotating mechanism also. And they kind of both work as a redundant systems because then if one fails, the other still kicks in. Now, one more thing that you want to manage is the force on the body. And because of this high pressure, we want some absorption, right? Some compliance. And there's this torsion bar, and even though it's made of steel, it does have some flex, right? And this is similar to your sway bar or stabilizer bar in your suspension, right? It flexes torsionally, and there is some twisting that is allowed. And therefore, even though it's rigid and it does hold you, but it still has some springiness in collision, right? I mean, the springiness is not that soft, but it's still something to just kind of reduce the force a little bit, right? Because remember, kinematics, Vf squared, V0, sorry, V final, yeah, minus 2a delta s. So, the acceleration, if you solve for that, Vf squared minus V0 squared divided by 2 delta s, right? And s is the distance. So this is a kinematic equation. Final velocity, initial velocity, acceleration, and distance. The same thing happens in acceleration or deceleration. So when you decelerate, same thing, right? You go from 50 kilometers per hour to 0. Okay? So 0 minus 50 squared, by the way, divided by 2 times delta s. And delta s is like, so if this is you and your body, your torso, right? And then you hit the seatbelt already restrain you, but if it has just a little bit more distance, it reduces the acceleration or deceleration that you experience. And deceleration, F equals ma, right? So if you reduce the deceleration, you reduce the force that you also experience. So this additional twist bar will give you just, maybe a few millimeters or maybe 1 centimeter distance on you moving forward, and that still helps. That still helps. Okay, you just want to be as soft as possible to reduce any broken ribs. I mean, the seat belts do break ribs. And then comes in the airbag. We'll talk about that. All right. Any questions on the seat belt and how it works? By the way, you still need your seat belt even though you have airbags. Do you know why? Do you know why you still need the seat belt? Police. I know, but theoretically, why do you still need the seat belt?
It's not going to fly out the window.
Huh?
If you crash, it's going to fly out the window.
Well, yes, it does provide some stability in terms of, you don't always have a purely frontal collision, right? Sometimes you have the corner collision and then you spin also and you'll get thrown out. Yeah. So, but even in just purely frontal, the airbag actually comes at you at a very high speed. We're talking like 200, 300 kilometers per hour of that balloon hitting your face. So actually, in a way, you're moving forward, and then this balloon moves against you, and you are actually increasing the amount of collision if you yourself are not slowed down first, right? So let's take a look at the the seatbelt. No, SRS. The official name for this thing is called SRS. You often see it on your dashboard, right? It says SRS. You know what it stands for? The airbag, SRS. It's called Supplemental Restraint System. And I think they intentionally call it that. So, Supplemental Restraint System. Why do you think they call it supplemental?
Because it's the secondary
It's not the primary, right? What is the primary?
seatbelt.
Seatbelts. It tries to prevent the notion that your airbag is your primary safety. It's not. So here goes. So the airbag is basically an explosive device, right? It's basically an explosive device, creating the gas in a very, very fast way. I mean, we're talking like a few milliseconds. So crumple zone, seat belts, and then the airbag kind of helps. You got the torsion bar, right? Now the neck is what you're trying to protect with the basically do that, right? So the seat belt holds the body. In some luxury cars, you also got the knee airbags because your legs can also slide out. But this is, so other than protecting the head, I mean, sometimes the seat belt will already hold you enough so you don't bow your head and bump the steering wheel. But still, even if you don't hit the steering wheel, the neck is going to snap this. So, oh, by the way, I forgot to mention the seat belt before. It also has a pre-tensioner. Some seat belts, I don't know how common this is. I think this is getting more standard these days. It actually pulls you. So there is a pre-tension depending on your deceleration. So if your computer knows that there is a very hard deceleration, immediately it snaps. There's a little explosive device or a motor to actually pulls you to the back, gives you more distance. Okay, because sometimes we drive like this, right? So it kind of pulls you back and then go into the back. So there is the pre-tension. But even with that, right? So if the pre-tension works, so you get more distance, seatbelt stops you, you are not going to hit the steering wheel, but still the neck injury will be very tough. And that's what the airbag is for. So the airbag actually inflates, I forgot the numbers here, so let me just unmute this for a moment.
1. The spring was not able to determine the crash accurately. 2. Crash of Joyson safety systems. First, he improved, sir.
This is the original design was using compressed air, but it's not going to be fast enough.
A steel ball is held in position with the help of a magnet. When a collision occurs, the car decelerates very quickly, but the ball gets separated from the magnet due to its inertia. The ball moves forward to close the circuit and sends a signal to the inflator. The second and his biggest contribution was the use of chemical explosives instead of compressed air.
So the original design is using compressed air, right? I mean, that's not going to fly. It's just too long. It takes too long. Now, this is the first explosive mechanism design.
Breed used a chemical called sodium azide for this purpose. The specialty of sodium azide is such that if this solid chemical is triggered by a temperature more than 300 degrees Celsius, it would rapidly and directly convert to a gaseous state. The 50 grams of sodium azide generated nearly 70 liters of nitrogen. This chemical is filled inside an airtight cylinder of the steering wheel. The electric signal sent by the ball sensor passes through a pyrotechnic device. It is a thin, resistant wire. When the current passes through it, it generates a temperature of more than 300 degrees Celsius. This causes the sodium azide to explode and generate nitrogen gas very quickly. This is able to inflate the bag within 30 milliseconds. These two breakthroughs made airbags possible for commercial use. This patented design of Breed Corporation was released by Chrysler in their Dodge Daytona model cars in 1988. This was a massive success, and all other car manufacturers started to implement similar airbag technologies. However, this design has two major drawbacks. First, the gas produced after the sodium azide explosion is
it
toxic.
absorbs moisture.
The sodium metal of the exhaust causes the trouble. Scientists were able to neutralize this issue by adding potassium nitrate and silicon dioxide. Do you remember the infamous Takata's 67 million airbag recall incident? This incident happened due to a notorious property of sodium azide. They absorb moisture content easily. If there is a leakage in the design stage or manufacturing, sodium azide will absorb moisture. After the moisture absorption, when triggered, the chemical will undergo violent explosions, causing the rupturing of airbags and shrapnel flying to the passengers. This is exactly what happened with Takata's airbags. Eventually, the company went bankrupt. To avoid such unfortunate incidents, the addition of a drying agent will be helpful, and strict quality control measures are required for components like airbags. Nowadays, sodium azide is replaced by guanidine nitrate as a gas generator. It is less toxic than sodium azide and is less explosive. It is not sensitive to moisture. Now we need not worry about the explosion and harmful gases. Even after these two design changes, the electromechanical sensor-based airbags suffered from one more issue. They would occasionally get activated even when they fell in a pothole.
I think I experienced this. My 93 Civic, we were doing the donuts in the snow and pulled the handbrake and we kind of spin. And then I think one of the curve, like the, you know what I mean by curve? Like this is the road and then there is the side. Yeah. So I hit that because everything is covered by snow, right? So I only see some trees. I'm in the parking lot, and then I got hit that. I hit one of the holes with that curb, and the airbag explodes. But I'm not hitting anything frontally. It's just my wheel hitting something, but the airbag explodes.
The reason? The electrical switches do not provide information about the rate of deceleration, which is necessary to determine the severity of the crash. That means it can't distinguish between a pothole and a crash. This is why, to detect the crash more accurately, nowadays, MEMS sensors are used with an advanced electronic control unit. This is a capacitance-based method, and the severity...
MEMS stands for micro electromechanical systems. Every accelerometer or sensors you have on your phone, they're all MEMS. They're on a chip, like really tiny chip. The chip has these micro or microscopic beams, right? So these blue bars, they are microscopic, and it acts like a spring.
If the crash can easily be determined. The capacitance-based method and the severity of the crash can easily be determined.
So do you see there is some deflection that happens, and as it slides, you detect some capacitance change here. and that's how accelerometers work. Accelerometers is how you measure G's, right? Crashes, acceleration, or also if you ever download the bubble level on your phone, you know, how you detect which way is down. It's also accelerometer. So accelerometers, rate gyros, they're all microscopic now, and it's very cheap. And it's just much more reliable than big mechanical balls. You got the dust in there and it doesn't work as good. So nowadays, all airbag sensors are MEMS. And they put a lot of these in different points on your car, by the way.
TU also takes input from the wheel speed sensors, gyroscopes, brake pressure sensors, and seat occupancy sensors.
So it's a combination of many different sensors. If nobody's sitting on the passenger, they will not activate the airbag. You can also manually turn off the airbag for the passenger seat if you put a toddler or a baby cradle there, a baby seat, right? Because the airbag will actually hit the baby's infant seat upward. So there are sensors here, and the purpose is that. The purpose is to disable the passenger airbag if you don't have enough weight of an adult there. So you have the seat occupancy sensor to turn on or turn off the airbag for the passenger. You got the rate gyro, you got the accelerometer, gyroscopes. You know what they measure, right? Gyroscope. Angular velocity. Okay, it measures velocity. So accelerometers measures the second derivative, and rate gyro measures the first derivative, which is velocity. So it measures omega. So it can measure the rotation, for rolls and all that. So you got gyroscopes, you got accelerometers.
The algorithm determines when to trigger the gas generator and how much to inflate the airbag based on the severity of the crash. The igniter ignites the explosive within 2 milliseconds and fills the bag within 20 to 30 milliseconds. The airbag remains fully open for 100 milliseconds. Now the airbag is ready to cushion you. The airbag spreads the impact's force over a larger area. It not only inflates, but also deflates to slow you down during impact. While deflating, it gives more time to travel. You can see.
So again, you want to increase the time and increase the distance, right? So the airbag actually deflates, so your head is actually slowed down even with more distance, right? Increase distance, increase time, everything you do to lower the force.
Two vent holes in airbags. The air vents out from these holes, and the airbag deflates to slow down your body. Do you know why the airbag will not work in some car models if you are not wearing the seatbelt? The speed of airbag inflation is huge, around 320 kilometers per hour. During this inflation, if you hit the airbag, that will be more lethal. So don't forget to wear your seatbelt so that this beautiful airbag technology can work.
Okay, any questions on airbags? Now, let's talk about a couple more. This is, I don't know whether this is safety, but we can call it safety. It's the TPMS, right? The TPMS, basically it's a tire pressure monitoring systems. And I don't know about you, but my wife does not know when the tire is flat. Honestly, if it's the rear tire, it's harder to detect. If it's the front, it's easier to detect. But a flat tire, you don't know what's going on other than costing you the entire tire, but also it's a safety hazard. So here is the tire pressure monitoring system. Basically, you have the sensor and the transmitter powered by a battery. it's gonna last a long time because it only take measurements like every, I don't know, few seconds maybe, or every minute. So it's designed to last many years. Not replaceable. You just replace the sensor. Basically, you have a barometer here and a transmission, wireless transmission system. So it's put behind the stem. You don't have to actually, but it's just a practical place to put it. Because you're not measuring the valve stem pressure. You measure the entire space. So you got a receiver here also. So this is wireless, right? It's all wireless. So that's the, in short, that's your TPMS. I think it's now mandatory in all newer cars. Here's an interesting video.
This is a tire pressure monitoring sensor, or TPMS. This small bolt right here attaches the valve stem to the sensor. It doesn't actually read anything from the valve stem. This is just perfect. And this is where your valve cap really came out, and this just slides off, and there's the stem. When you fill your tire up with air, you put it in here, and it doesn't come out the bottom. It comes out this hole and this hole. There aren't any screws that hold this case together, so I'm going to have to break it apart. Interesting, it looks like these are melted together. Alright, the actual sensor is on a microchip. I'm going to see if I can get this chipboard off. Now, most of the size and most of the weight too is the battery that actually powers this thing. Although they obviously don't design these to be serviceable, the battery in here is a CR2032, which is actually a very common battery size. Odds are, if you can remove it, very common. Two here, loose. So let's test the battery out.
So,
inside.
the sensor is basically a barometer.
Hopefully this satisfied your curiosity about what these look like on the inside.
You see that tiny hole? So that's where the air pressure is measured. Okay. Now, I found this in one of the
This
videos.
is an inertia switch.
To be honest, I'm not aware of this thing before. Are you aware of inertia switch? It's kind of, once you bump it, it will pop out and it's going to cause some alerts. I'm not aware of it.
In the up position. Not all of them are designed this way. In ideal situations, its entire life, it stays in the on position, which is just how it is here. You'll notice there's a red button on here, and it's in the down position. As you're driving along, this is allowing electricity to flow through it. This particular one is used on some Ford models, and it's wired up to the fuel pump. The reason why this is wired up to the fuel pump is, in the event of a collision, your fuel lines may break, and your fuel pump may be still on, pumping fuel out into the open. If that catches on fire, you're in for a real bad time. So when your car gets hit, the switch activates, and now this button is in the up position. Not all of them are designed this way. Some of them are self-resetting, and some of them are one-time use.
I don't know, but this exists. It's to stop the fuel pump. I mean, I can see the logic. It's just that, you know, then that means that it has to be pressed to reset it. I don't know. Well, anyways, okay. Well, let's talk about active safety systems. And here's an overview. I don't want to go through every single one of them. I think it's pretty obvious what they do.
Hi, and welcome to another in our series of Start Rescue driver information videos. In this video, we're going to help you understand your car's onboard safety systems. Modern cars are loaded with clever state-of-the-art technology designed to keep drivers, passengers and even pedestrians safe. But with so many acronyms flying about and different brands using different terminology, It can be hard to understand what your car is capable of. So, let's take a look at some of the most common safety systems. Collectively, these are often referred to as Advanced Driver Assistance Systems, ADAS, or Safety Assists. But before we do, always remember to refer to your car's handbook for full deep emergency AEB.
So first there is the automatic braking.
It's a system that can detect potential forward collisions and automatically apply the brakes to mitigate the dangers. Usually you'll hear an initial warning sound or see a visual alert prompting you to take action before the system steps in to apply the brakes as a last resort. Adaptive cruise control.
Now this is not exactly safety, I mean it's a feature, but I guess the safety side of it is it kind of tells you to maintain a certain safe distance, right? Braking distance.
While standard cruise control will maintain a precise speed as programmed by the driver will need to manually adjust his or her speed as traffic builds or eases. Adaptive cruise control, on the other hand, constantly reads the road ahead and will accelerate or decelerate as necessary to maintain the design speed set by the driver where possible, depending on how busy the road is. Assistive steering. Assistive steering is one of the most advanced autonomy features widely available today, and as the name suggests, provides support for the driver, helping them steer correctly. The system is designed to assist a driver in keeping to their lane. It is absolutely not designed to steer the car automatically, made as hands on the wheel.
So you're still required to hold the steering wheel. You'll detect whether you're still steering it or not. At times I'm a bit lazy and I open my water bottle and go while the lane keeping assist.
Sometimes dangerous too.
Yeah.
Because one time I was driving the BYD, the new BYD has a
Uh-huh.
but as a driver, usually if an incoming car, you know if you're gonna collide or no. So you accelerate or you decelerate depending with your experience. But
Right.
the car doesn't know the judgment of a human being.
Yes.
It detects the distance and then apply the brake. So
Mhm.
me, I was going through a stop light, a red light. I already make the judgment, but the car applied the brake instantly, and the car behind me just bumped
Ah.
into me. So it wasn't like a big bump, but still, it applied the brake without me pressing the brake. So this one is pretty dangerous.
It's too anticipative,
Yeah.
right? It's too conservative, and yeah, it can cause unnecessary crash. But I think the driver assistance can be turned off. I
They
think.
can be there.
Yeah, I turn off some of them. I do not turn off my automatic emergency braking, but I turn off the blind spot beep. Is just too annoying because come on, it's Indonesia. Somebody most likely is in your blind spot at all times. If not motorcycles, like anything, right? Anything.
The emergency braking. The once I was driving my cousin Mercedes,
Uh-huh.
new C. Because I didn't know, he didn't tell me about this sensor.
Right?
And then there's a motorcycle it's a kind of traffic. We are going 40, and then the motorcycle just
Yeah.
and then the car just braked.
Do an emergency
Yeah.
brake.
And then the car behind me
Hit.
almost
Almost hit you.
even there. So in Indonesia, I don't think it's still
Yeah, yeah. They have to have a different setting on it, I guess. I mean, it's
Advanced
fine.
AI.
advanced.
Advanced AI to be able to.
So yeah, it has to be a bit more conservative. I mean, I think it's still useful to reduce the collision, maybe. So what I would do as an engineer, I would set it so it's quite in a very extreme circumstance only that it does emergency braking. And yes, it will not prevent a crash because you're a bit too late. but it's probably fine. It still reduces the collision speed, no matter what, right? Because you still reduce it before you hit. So yeah, I think the ADAS parameters going to be different for Indonesia. Here's a great one, ESC, right? Electronic Stability Control.
Has been fitted as standard on all new cars in the UK since 2014 and builds upon the protection offered by ABS. Often when a driver takes evasive action in an emergency, it can send them into a slide or spin. ESC employs wheel sensors to detect a loss of control and can automatically apply small amounts of braking to individual wheels to regain stability.
So this is enabled by the ABS technology, because ABS puts the electrical actuator on your brake fluid, brake lines, and so it can basically brake one or more of your wheels by the computer.
Lane assist. Lane assist systems are now commonplace on new cars and help to prevent accidents that occur when a driver veers out of their lane. A lane assist system monitors the road and reads road markings and understands where a driver should be on the road.
Use this a lot, lane keeping, lane assistance. I use it sometimes.
Road. Blind spot information system.
No, I don't use this. Someone is always on my blind spot. I assume that.
Many accidents happen when drivers fail to notice another vehicle behind them in their blind spot. Blind spot warnings minimise the risks of that happening. Usually, drivers will be warned of an object in their blind spot by a bright light in their rear mirror. This warning may also be duplicated on the instrument cluster or head-up display. Rear cross traffic assist.
Now, I think this one is very useful, especially in Indonesia. You know, again, you just don't know. So you're backing out, or you're going out from your parking spot, and somebody just.
Rear cross traffic assist systems are designed to protect against accidents that occur when a car is reversing out of a parking spot. It detects vehicles, or in some cases pedestrians, approaching from either direction, and either gives a warning or applies the brakes. Tyre pressure monitor. Most modern cars are also fitted with sensors to measure tyre pressures. These will let you know whether your vehicle's tyres are under or overinflated, both of which can have an impact on handling, braking distance and economy. If your car shows slightly underinflated tyres, visit a garage at your earliest convenience to adjust your pressure or use a tyre pump or compressor.
I think we didn't talk about tires yet. So what is the advantage and disadvantage of, not the advantage, but the disadvantage of under versus overinflated? So why do you not want an underinflated tire?
It would be like most of your tire will be on the ground. Usually.
So what's the downside? What happens underinflated?
More drag.
Hmm?
More drag.
More drag.
Yeah, like more.
Oh, drag, yeah. Rolling resistance, right? So in extreme underinflation, you're going to lose some traction. So this is your wheel, right? You're gonna lose traction in the middle, but this is only for extreme underinflation. But for moderate underinflation, you actually gain more traction, but rolling resistance. What about overinflation?
You only get like a bit of
Yeah.
traction.
So you are reducing your traction, right? So you're reducing your traction here, and tire wear is uneven. Okay, under inflation, you got more tire wear on the outside. Over inflation, you got more tire wear on the middle. Saves fuel economy though. Not by much, but
However, if you have a major loss of pressure caused by a puncture, you should pull over to the side.
Okay, so now ADAS also kind of relates to automation
An
levels.
analysis revealed that about 94% of accidents were caused by human error and the remaining by the environment and vehicle's path.
So these are the sensors that enables ADAS, and this video also explains the automation levels because of that, in relation to that.
Radar waves to detect objects and measure their distance and speed. They are excellent for detecting other.
So radar or LiDAR for the laser ones, actually is a technology to measure objects and objects' distance. So that's part of your sensor that you need to do this driver assistance.
The vehicles and objects in the vehicle's path. LiDAR sensors. It emits laser beams and bounce off surrounding objects, creating a detailed 3D map of the environment. This allows for precise object detection and mapping.
By the way, not all LiDARs are 360. You can have a one-dimensional LiDAR also, which I think is what you have in the forward radar.
Ultrasonic sensors use sound waves to measure distances to objects in close proximity to the vehicle.
This is your parking sensors.
They are often used for parking assist systems, alerting drivers to nearby obstacles.